Hello, today we're going to solve a fascinating system of nonlinear equations. The system we're looking at is x squared plus y equals 37 and y squared plus x equals 37. By the end of this video, you will be able to solve this specific system and understand the powerful technique we'll use to find all its solutions. Our main objective is to find all pairs of numbers, x and y, that satisfy both equations simultaneously. At first glance, this system might seem tricky because of the squared terms. A common first thought is to use substitution. Let's try that. From the first equation, we can isolate y. Y equals 37 minus x squared. Now, we substitute this expression for y into the second equation. This gives us the quantity 30-7 minus x squared plus x equals 37. While this is a valid step, expanding this expression would lead to a polynomial of degree 4, which can be very difficult to solve. So we'll need a different approach, one that exploits the special symmetry of this system. Notice the similarity between the two equations. If you swap x and y, the system looks exactly the same. This swapping symmetry is a key hint. Because of this symmetry, if AB is a solution, then BA must also be a solution. Let's use this property. We'll take our two original equations and subtract the second equation from the first. This simplifies to x squared plus y squared minus x equals 0. Let's regroup the terms to make factoring easier. We'll group the squared terms and the linear terms together. So we have x squared minus y squared plus y minus x equals 0. The term x squared minus y squared is the difference of squares, which factors into x minus y times x plus y. Now, let's look at the second part, y minus x. We can factor out a negative 1 to get minus x minus y. This transforms our equation into x minus y times x plus y minus x minus y equals 0. Notice the common factor here. Both terms have an x minus y. We can factor it out, leaving us with x minus y times the quantity x plus y minus 1 equals 0. So, we've broken down our complex problem into two much simpler cases. For this product to be 0, one of the factors must be 0. This gives us two possibilities. Our first case comes from the factor x minus y. Case 1, x minus y equals 0, which means x equals y. Now we substitute this back into one of our original equations. Using the first equation, x squared plus y equals 37, and replacing y with x, we get x squared plus x equals 37. This is a simple quadratic equation. Let's rearrange it into standard form. X squared plus x minus 37 equals 0. Since this doesn't factor easily, we'll use the quadratic formula to find the values for x. The quadratic formula states that x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Here, a is 1, b is 1, and c is negative 37. Plugging in the values, we get x equals negative 1 plus or minus the square root of 1 squared minus 4 times 1 times negative 37, all divided by 2. Simplifying, we get negative 1 plus or minus the square root of 1 plus 148 all over 2. This is negative 1 plus or minus the square root of 149 all over 2. We have two solutions for x. Since we are in case 1 where x equals y, the solutions are pairs where the x and y values are the same. Our first two solutions are the pair where x and y are both minus 1 plus square root of 149 slash 2, and the pair where x and y are both minus 1 minus square root of 149 slash 2. Now let's examine our second case, which comes from the factor x plus y minus 1. Case 2, x plus y minus 1 equals 0. Which means x plus y equals 1. We can rearrange this as y equals 1 minus x. We will now substitute this into our first original equation. Plugging y equals 1 minus x into x squared plus y equals 37, we get x squared plus the quantity 1 minus x equals 37. Again, this is a quadratic equation. Let's simplify and put it in standard form. This becomes x squared minus x plus 1 equals 37. Subtracting 37 from both sides gives us x squared minus x minus 36 equals 0. We'll use the quadratic formula again to find the values of x. Here, a is 1, b is -1, and c is -36. Substituting these values into the formula, we get x equals 1, plus or minus the square root of -1 squared minus 4, times 1 times -36, all divided by 2. Simplifying, this is 1 plus or minus the square root of 1 plus 144, all over 2. This equals 1 plus or minus the square root of 145, all over 2. Now we have our x values for this case. To find the corresponding y values, we use our relationship for this case. Y equals 1 minus x. For the first x value, y is 1 minus the quantity, 1 plus square root of 145 / 2, which simplifies to 1 minus square root of 145 / 2. For the second x value, y is 1 minus the quantity, 1 minus square root of 145 / 2, which simplifies to 1 plus square root of 145 / 2. These calculations give us our final two solutions. Our third solution is the pair, 1 plus square root of 145 / 2, 1 minus square root of 145 / 2. And our fourth solution is the pair, 1 minus square root of 145 / 2, 1 plus square root of 145 / 2. So, by splitting our problem into two cases based on the symmetric subtraction, we were able to find 4 distinct solutions. Let's recap all the solutions we found. We have 2 solutions from the x equals sign y case and 2 solutions from the x plus y equals sign 1 case. A useful way to visualize this is to consider the graphs of the 2 equations. The first equation, y equals 37 minus x squared, is an upside-down parabola. The second equation, x equals 37 minus y squared, is a parabola that opens to the left. The solutions we found correspond to the 4 points where these 2 parabolas intersect. Today, we successfully used the symmetry of a nonlinear system to simplify it, find 2 cases, and then solve a quadratic equation for each case to find all 4 solutions. This technique of adding or subtracting equations is incredibly powerful for symmetric systems. Thank you for watching.